Hey guys, welcome back to Spark AR Scripting. In today's episode, we're going to be going over reactive programming, what that actually means, and how that compares to using patches in Spark. I'll also cover last week's script in a bit more detail and show you how that compares to patches as well. So if you haven't already seen the episode from last week, check that one out first because this one will build on top of that. So in last week's episode, we finished with a red pulsing quad on the screen, and we wrote the code for that, which was basically just this over here. I'll cover this in a bit more detail, but first, just want to talk a little bit about what reactive programming actually means. So Spark is basically a 3D application similar to a game engine, which means it has to run several times per frame, most likely 30 frames per second. So that means it has 1/30 seconds to render the whole scene, which equals 0.03 seconds. In terms of milliseconds, that means it's 33.3 milliseconds. So it has this much time to render the whole frame, and that means it has to run all the scripts and update all the objects and render the frame all in this time. So that's not a lot of time. So basically it needs to run pretty fast. So let's just see what the code for a game engine looks like. So a game engine is going to be something like this. It's going to have while game is running. So this isn't really actual code, so don't expect it to compile anywhere. I'm going to do update game and render game. And the update game is going to be basically a function, update game, which in case we have scripts, it's going to do something like update scripts. And let's say we're using JavaScript for our language, so we're going to have a script.js file somewhere, which has an update function. And what that's going to do is, let's say we have a sphere object, scene.find sphere. And then to update it, it's going to do sphere.position plus equals sphere.velocity. So every frame, it's going to update the scripts, then it's going to come inside here. And then when it's inside the script, it's going to go and run this, which is scene.find sphere, which means it's going to have to go back into the engine and try and find the sphere object and return it to the script. Then it's going to take the position of that sphere object and add its velocity in. So basically, every frame is going to be going into the script, back into the engine, and back into the script, depending on how the code is set up. So over time, this adds up and it starts to get a bit performance intensive. And instead, the other option is reactive programming. And the way this works is while game is running, it's still going to do update game and render game. But basically, there's going to be a function load game. And what that's going to do is load scripts. And this is going to build a bunch of connections, which is used to update the game later on. So it's going to do something like build patch graph. And then in the script over here, you could have a function load, or in our case, this was called main. And what that is going to do is const sphere equals scene.find sphere. Then it's basically going to create, instead of just directly adding to the sphere's position, it's going to create a signal, which is going to be add sphere.position sphere.velocity. And this is going to return a signal. So let's say we store that signal equals this, and then we can do something like sphere.setPosition signal. So basically when it loads the game, it's going to go inside the script and run all this code, which will generate a bunch of connections from these signals and create a patch graph for you. And then basically in the update function, it's going to do run patch graph. So instead of going to the script every frame, it's just going to do that at load time. Then the script is going to tell it how to create all these connections, which will be used to build the patch graph. And then in the update, it's just going to run the patch graph. So it's not calling into your script every frame. So basically, under the hood, it's doing the same thing as you creating a patch graph in the patch editor, which is why scripting is very similar to creating a patch graph, because it's based on the same principle under the hood. So this is basically an advantage, especially on older phones. Like Spark supports some older Android phones which don't have a lot of processing power, so it's much faster to just run the graph instead of going into the script every frame. The disadvantage is, instead of your scripts looking like a regular programming language, they're going to look more like a patch graph. But if you're used to patches already, then for you that's more of an advantage. So hopefully that made sense. I'll walk us through our patch from last week now and show you how that relates to this, what we've just learned here. So it should become a bit more clear after that. Alright, if you look at this code, all it's doing is basically just creating a bunch of connections. First we call shaders attributes, which is going to return a signal, and it's going to store that signal inside this variable called UVs. Then here, so let's say we call this signal 1. Inside here, it's going to create signal 2, which is just a multiplication node which takes in time.ms and 0.001. So as it's going through this, it's creating all these signals. Then again here we got signal 3. Actually, it'll be easier if I just show this to you in the patch side. So I'm gonna recreate the patch we had from last time. So again, let's start with the top. So we have vertex attribute, so we need that. Now what this is doing is creating a signal which gives us the texture coordinates. That signal is this thing. Then what we do is we have reactive.mul times.ms and 0.001. So let's go inside. I think that's probably it. Runtime. Does it say what runtime does? So this is in terms of seconds, but let's just assume that it wasn't. Then what we would do is create a multiply, and we would multiply this by 0.001. So if you look at this, we have time.ms, which is over here. Then we create a signal. Anytime you use the reactive framework, it's gonna create one of these nodes for you. So in this case, it's gonna create a multiply node, which is this thing. And then we're giving it time.ms, which is here, but we just get it from the time module, and the other argument for the multiply is 0.001, which is exactly the same thing as here. And then that returns another signal, which is here. Then we have another signal 3 over here, which is reactive.abs and reactive.sign of this thing. So what we just do is create an absolute, and then we create sign. And what I had is reactive.sign CT. So we already have CT. Then we do reactive.sign, and basically what we want to do is, so we have reactive.abs and sign. So we take the sign of CT and then we take the absolute value of that. So how would that look here? So we take the sign, and then after that we feed it to the abs. So here you can see the runtime goes into a multiply, goes into a sign, and then it goes into the absolute. So similarly here we have a multiply, so we have the runtime, which goes into the multiply with this value, which goes into the sign, which goes into the absolute. And it's the same thing here, multiply, sign, absolute. And then you have another signal out here, which we call signal 3. And now what we do is color is shaders.texture sampler. So let's create a texture sampler, and in this case we need the textures as well. So I'll bring in the camera texture, and material 0 was from here. So again, in script, this is going to create signal 4. So now what we had is modulation color, and that is just going to be, I actually don't know how to create a color. I think it's just pack 4. Yeah, it's probably pack. So we basically take the curve and put it into this thing here. So there you go. Now we have, so I want this to be a 4 channel, so that we have 1 for the alpha. And what we can do is so first we sample the camera texture. And so this is why I don't like patches, because basically half the time you're just spending moving these things around, and it's just a bit of a waste of time, if you ask me. Because you'd much rather be creating the logic for your effect than moving these nodes around. Okay, so now we go back and we have the final color is reactive.mul color and modulation color. So again, if we have a mul in here, we just need to create a multiply node here, and that's taking in these 2 colors. So we give it this color and we give it this color, and basically we just feed that into the texture slot. So let me just say this again creates another signal 5, and then we got another signal 6, and then this is just set signal 6 arrow to material. So based on the signals we create, it's going to try and create a patch graph for us from the script, and then finally when we output it to the material, it's going to use that to generate the final patch graph. This works a bit different when you're in the shaders module, but I'll explain that in the next episode. But for other types of reactive code, this is basically what it's doing. It's interpreting your script as instructions to generate a patch graph under the hood. So what I'm going to do is comment out our script, so it's not setting the texture slot to the final color anymore. And we just have white, so what I'm going to do is send this into the diffuse color. And so basically, like I said, this was seconds, so we actually didn't need to multiply it by 0.01, so let me just set it back. And there you go, we have the exact same thing in the script. And this is actually equivalent to what the code you wrote here. Hopefully it's clearer now that all we're doing in the script is just creating these connections, which is basically just means you're creating a patch graph in the text editor. So yeah. And just to show you that it's running the patch, I'll just modify this. So now we have the blue channel in there as well. So all these nodes you're creating, they're going to be in the reactive module. So basically you're going to be using this a lot. Like, just imagine the number of times you create all these nodes in a patch. So in the script it's going to be similar. So what I usually do is rename this to R, and just to be consistent, I rename this to M, and I rename this to S, and rename this to T. Because these modules end up being used a lot, so you want to type less. And then diagnostics is D, so now we just do d.log, this becomes m.get, and this becomes t.get, and all the shader stuff is s dot whatever, and the reactive is going to be r dot. So it just makes your scripts easier to type. That's just a quick tip if you're going to be writing scripts. That's an easy way to type less. Okay, so before we go, I just wanted to show you one thing. Like I said, over here we have this word function, and if you want to create a function here, let's say we want to move all this to a function, we just select all these nodes, do group, and then call it modulate, right? So now we have this group called modulate, and I believe you can give it inputs and outputs, which is similar to a function in Spark. So now we have a modulate group here, which is used to modulate the texture color bar. Similarly here, we can create a function modulate, which will do the same thing. So we're not giving it any inputs. We could move the time outside. So what that'll do is, so basically we just take this and we move it here, and then we also had this guy here, and then all this does is return the modulation color. So that's how you return an output from a group, which is basically this thing. So now what we have is, instead of, so we just create constant modulation color equals modulate. So now all we've done is created a group in code which has this stuff we added in there, and it's gonna give us the modulation color, and we're effectively at the same point. Now let's say you want to make this runtime an input, so I can take this out, go back here, give it an input, which is, let's say it's a time, and we do runtime and we set it as the input. So now basically we have, and inside here we're gonna have to use the input as one of the values. So there you go. And similarly here we just make time an input, and instead of this we just use time and we just pass in time.ms, and that's the same thing. And you can see it's much easier to do an edit like this in script as well, because you don't have to go inside rewire your nodes. It's just typing and editing a bunch of text. And then, so let's just delete this and see if our script's still working. So if I uncomment this out, yeah. So what I'm going to do is show you how to take a patch and convert it to a script. So I haven't really created any patches of my own because I always use scripting. So let's just use something from the AR library. Okay, so let's just go to patch assets, I think, and shaders might be nice. Duotone. Let's just do a simple Luminance because it should just be like one line of code or something. Okay, so we just drag this in here, and what Luminance does is just takes an RGB image and gives you like a brightness value, so a single channel output for that RGB value. So let's just go inside. So basically, if you're using a patch asset like that, that by definition is a function because it's been grouped. So in this case, we have a function named Luminance, and it takes in an input, which is a color. So in the patch here, you can see 3 values here, but in the script, you're just typing the word color. So basically, when it's parsing your script, it figures out what input you're passing in and tries to match it to the arguments. And if it's not able to do that, it'll give you an error. So basically, at runtime, it'll figure out what value you're passing in, so you don't have to tell it what the type is. You do in other programming languages, but I think JavaScript is a bit more lenient. Alright, so let's just go inside the Luminance function, and then we can convert it to our script. Okay, it's just, sure. So basically it takes the color, it unpacks it, and then it does a bunch of multiplies, and it does a bunch of adds, and then gives you a Luminance value. Okay, so let's just translate this to code. So what we have is, we have this situation here. First we unpack it into XYZ, then we multiply the X by this number, we multiply the Y by this number, we add those two together, we multiply the Z by this number, then we take the sum of the first 2 multiplications and add it to this multiplication. So you do 2 multiplies and an add, then do another multiply and an add. So in code, you don't really need an unpack because you can just access the color directly using color.x, color.y, color.z. So we take, so the first multiplication let's just call it A equals r.mul, and then we give it color.x and we multiply it by 0.2125. Then we got constant b equals r.mul color.y, sorry, with 0.7154, and then we got constant c equals r.mul color.z with 0.0721. Okay, so we do two multipliers, then we do ab equals r.add a comma b, and then we got abc equals r.add ab with c. So now we've done this first add, which is taking two multiplications and storing them into AB, so it's adding the first two, and then we take the first two, the sum of the first two, and add it to C. So we take these two and add it to that. So this is basically doing the same as this. And then finally we can just return ABC, and this will effectively do the same thing as what we had in the patch. So basically we're in a patch group, which is just creating a bunch of reactive signals, linking them together, and then returning the final output of our signal. One interesting thing to note is that instead of all of this, you can actually do luminance using a single instruction, and that is the dot product. I'll explain the dot product in a bit more detail later. For now, it just does a component-wise multiplication of two vectors and then adds the individual components together. So what we can do is just directly return r.dot, and then we have the color, and create a new vector 4 which has these components 2125, 0.7154, 0.0721, and we're going to need a fourth component 0. So what this will do is take color.x multiplied by this, color.y multiplied by this, color.z multiplied by this, and then color.w and multiply by this, and then add all of those together and then return the sum, which is exactly what we're doing here. So I can actually just delete all of this. So yeah, it's much easier to type just one line instead of all those instructions, and it's actually much faster as well to do it this way, because the shader units in hardware are much more optimized to do dot products instead of all those individual multiplies and adds. I'll cover this in a bit more detail in the next episode, which is going to be about the shaders module. And just to note, in case you're curious, these numbers, basically they're 21% red, 71% green, and 7% blue. So as you can see, they're weighted heavily towards the green, and that's because our eyes are much more sensitive to the green shades, and that's just how our eyes have evolved over the years. Basically, we have a lot more green receptors in our eyes than the other colors, so this function is also weighted towards the green. You can read up a bit more about this if you want. Just search for grayscale on Wikipedia or the grayscale operator and you should find some information. For now, let's just take the luminance and apply it to our effect. So what we can do is create a variable here, const.lum, which calls the luminance function and passes in color. So we take this 4-channel color, pass it to the luminance function, which applies the dot product and converts it to a single channel brightness value, which is stored in this variable. So now what we can do is just, firstly, instead of just outputting the modulated color, we can just directly output the luminance value. So we have to replicate it to 4 channels. So we do pack4 lum1, and then if you go back to Spark, there you go. So now we see a grayscale image of our scene. So okay, so now what we can do is take the luminance value and pass it into the modulation function. So in the modulate function, we do time.ms and lum, and then we can just declare it here. So now what we can do is, first we can just set the curve to be the lum value to see what that gives us. So there you can see it basically highlights the bright areas and darkens the dark areas more. So it gives it this bit of sci-fi look to it. So now what we can do is just, instead of that, I suppose we can just do final modulation equals r dot add, and then we can do, so we create a 4-channel Lum 4, pack 4, Lum 1, and then we just add to the modulation color, we just add the luminance value. And now we can, instead of outputting the modulation color, we output the final modulation. And that'll give us this stylized effect where it's adding the luminance to the scene. So it's got this artistic glow type look to it. Okay, so there you go. We've basically gone both ways. We've taken a patch, converted it to a script. We've taken our script, converted it to a patch, and I've shown you how functions relate to patch groups and how similar patches and scripting is in Spark because of the reactive paradigm. So hopefully it should be much more easier for you now to get into scripting. If something wasn't clear, make sure to add it to the comments below and I'll get back to you with a better explanation. Alright, I'll stop it at this for now. As mentioned, if you have any questions, just drop them below and hopefully you learned something. And don't forget to hit like and subscribe if you found this video useful. In the next episode, I'll be covering the shaders module in a lot more detail and show you how all that stuff works. So stay tuned and I'll see you guys next time.